Turbomachines. Turbomachines are devices that exchange energy from the flow of fluids using the action of rotating blades. The fluid involved can either be a gas, vapor, or a liquid. Depending on the direction of the fluid motion, turbomachines can be classified as axial flow, mixed flow, or radial flow. To calculate the work done to or the system, we have to consider the fluid velocity given by the relative velocity and the blade velocity. With this information, we can construct the velocity diagram and determine the flow of the fluid and the work on a pump and on a turbine. The flow on a pump is given by the force of the motion and the blade when they are in the same direction. Thus, the blade does work on the fluid. In the case of a turbine, the fluid flow through it moves in the opposite direction of the blades. Thus, the fluid does works on the blade. Momentum considerations. Turbomachines involve the rotation of a rotor about a central axis. Thus, angular momentum and torque are appropriate to be discussed. A series of particles passes through a rotor, thus the moment of momentum equation applied to a control volume is valid. The one-dimensional simplification of flow through a turbomachine rotor can be given with part 1 as the inlet and 2 as the outlet by the Euler turbomachine equation, where the shaft torque is applied to the contents of the torque. As seen, the torque of the shaft is directly proportional to the mass flow rate and also depends on the tangential velocity. We can recall that the power of the shaft is related to the torque and angular velocity, and the power and the work can be calculated from the equation below, where the speed of the blade is given by U, the absolute fluid speed is V, and the fluid speed relative to the blade is W.
Axial flow pumps are pumps with flow parallel to the axis of rotation of the shaft. You're able to move large volumes of fluid. The impeller in this pump moves the liquid on a parallel path to the pump shaft, as you can see on the design drawing. The fluid mainly moves by propeller action of the impeller vanes. This impeller uses only a small amount of centrifugal force to move the fluid. As a result, the axial discharge of an axial flow tends to be lower than that of a radial flow pump, but it's able to move larger quantities of liquid. This is the new General Electric turbofan engine that will be used in the new Boeing 777X aircraft, and it features an axial flow compressor. The compressor is a key component of the engine and is responsible for compressing incoming air before it's mixed with the fuel and ignited in the combustion chamber. The axial flow design is common in jet engines and is known for its high efficiency, which helps to improve the overall performance and fuel efficiency of the engine. Here on this drawing, you can see how the flow is axial to the engine. Mixed flow pumps combine the characteristic of axial and radial flow pumps having high discharge pressures and still move large quantity of fluid. They are typically more efficient than axial flow pumps at higher pressures and provide better performance in low head applications than radial flow pumps. They're commonly used in applications where a balance between flow rate and pressure is required. Here on this diagram, you can see the flow will enter radially but exit axially. This is the Aerojet Rocketdyne F1 engine, which was used in the Saturn V rocket that carried NASA's Apollo mission to the moon. It is a rocket engine that features a turbopump-fed system with both radial and axial flow components. The axial flow pump was used for the fuel, which was kerosene, while the radial flow pump was used for the oxidizer, which was liquid oxygen. This combination of radial and axial flow design helped to achieve the high thrust and performance required for the Apollo missions. The F1 engine is very potent. As you can see on the tech notes, Every second, a single F1 engine can generate 1.5 million pound force of thrust. Here you can see a picture of NASA testing these devices, and a fun fact is that the F1 still holds the record for being the largest liquid rocket engine ever made.
Radial flow. In this type of flow, fluid moves radially from an inlet or outlet through the blades, in this case of a pump, adding a radial component and a circumference component to the fluid velocity. One of the most common type of radial flow turbo machine is a centrifugal pump with many applications, from the water supplies in residential areas, fire protection system, sewage and slurry disposal, manufacturing operations, oil and gas operations. This helps to move fluids from different parts of the process, in whether it's water distillation plants, petrochemical plants, mining industry, fracking, among others examples. At the heart of this pump, we have the impeller. The impeller consists of a number of blades, usually curved, arranged in a regular pattern around a rotating shaft. As the fluid flows radially from the eye or the center to the periphery or the edges of the blades, energy is added to the fluid by rotating blades, increasing both the pressure and the kinetic energy. As the impeller rotates, fluid is sucked in by means of pressure gradients. Fluid flows radially through the eye to the edges of the blades to what is called a casing, a housing of a volute. For the simplest type of a centrifugal pump, the fluid is discharged directly into the stationary ball-shaped casing with an increasing area in the direction of the flow. This helps to reduce and also produce a more uniform velocity distribution of the fluid moves from the eye to the discharge opening. This reduction of kinetic energy favors an increase in pressure. The type of impellers are enclosed, semi-open, and open impellers. These can be used depending on the properties of the fluid and the efficiency.
Turbines are devices that extract energy from a flowing fluid. The geometry of the turbines is such that the fluid exerts a torque on the rotor in the direction of its rotation. The shaft power generated is available to drive the generator or other devices. Turbines can be classified into impulse turbines and reaction turbines. These classifications are based on the mechanism of the fluid interaction with the turbine blades. In an impulse turbine, the force of the blades is produced solely by turning the fluid without appreciable pressure drop in the blade passage, with all of the pressure drop occurring in a fixed nozzle. The Pelton wheel is a classic example of an impulse turbine. The total head of the incoming fluid is converted into a large velocity head at the exit of the supply nozzle. The Pelton wheel is essentially an improved water wheel. It is most efficient when operated with a large head, which is converted into relatively large velocity at the exit of the nozzle. The space surrounding the rotor is not completely filled with fluid. It is the impulse of the individual of fluid striking the buckets that generates the torque. In this image, we can see a Pelton wheel, which is preferred turbine for hydropower, where the available water source has relatively high water head at low flow rates. Next, a reaction turbine uses the pressure as well as the velocity of the moving water to rotate. Some of the fluid vane force is from fluid turning, and some of the force is a reaction of the fluid relative to the vane. The pressure drop occurs in both a fixed nozzle and the moving vane. The rotor is surrounded by the casing, which is completely filled with the working fluid. Reaction turbines can be classified into two: the Francis turbine and the Kaplan turbine. Francis turbines are typically radial and mixed flow turbines. Francis turbines are usually mounted with a vertical shaft to isolate water from the generator. This facilitates installation and maintenance and can achieve 95% efficiency. On the other hand, Kaplan turbine is an efficient axial flow turbine with adjustable blades. The absolute velocity of the water leaving the rotor is essentially without a tangential component. Hence, the rotor decreases angular momentum of the fluid. The fluid exerts a torque on the rotor in the direction of rotation, and the rotor extracts energy from the fluid. As a conclusion, impulse turbines are best at low specific needs, that is, when operating with large heads and small flow rate. Axial flow turbines are most efficient type if the head is low and if the flow rate is large. For intermediate values of specific speeds, radial and mixed flow turbines offer the best performance. Thank you.